All right, we're going to try a different one now. This one is going to have irrational zeros. What that means is we're going to need the square root in this one. Everything else will stay the same, but this one is just going to include some irrational answers, meaning we're not going to get perfect real numbers, we're going to get some square roots. All right, so the first thing we want to do is our RZT theorem, same as before. That's the rational zeros theorem, where we take the factors of the end constant, 3, and we compare them to the factors of the leading coefficient on the 4. So we do this, we say P over Q, where P is all of the coefficients of the 3, and Q is all of the, did I say coefficients? Factors of the 3, and Q is all the factors of 4. So if we look at 3, 3 is evenly divisible by 1, so we'll need a positive negative 1, and it's also evenly divisible by 3, so we'll need a positive negative 3. When we look at Q, that would be all of the factors of 4, so that's going to be a positive negative 1. 4 is also divisible by 2, so we'll need a positive negative 2. And 4 is divisible by 4, of course, so we'll need a positive negative 4. If I if I list all of these out, that would be a positive 1 and a negative 1, a positive 3 and a negative 3. And that exhausts all my whole numbers. Everything else from here on out is fractions, but I'm not going to let it scare me. I'm just going to keep using the process. So it's going to be a 1 over 2 positive, and I'll also need a 1 over 2 negative. Then I will need a 3 over 2 positive, and a 3 over 2 negative. I'll need a 1 over 4 positive and negative. So negative 1 over 4. And I'll need a 3 over 4 positive and a 3 over 4 negative. This gives me 12 possible zeros that are real numbers. I need to narrow that down a little bit more if I can, so I'm going to try Descartes to see if that will help me. D-E-S-C-A-R-T-E-S, Descartes. And Descartes' rule of signs is just a way of analyzing the signs of a polynomial to determine if I have positive and negative roots here. So if I do, I want my eraser, there we go. Okay, so if I look first at P of X, the terms are positive, negative, and positive. So positive, negative, and positive. This is not just one, but two sign changes. The positive goes to negative, the negative goes to positive. So I will have two sign changes there. And if that x is actually a negative x, so we'll assume that it's a negative number. So we'll write negative x to do that. Then negative x to the fourth would give me 4 negatives, and it would stay positive. It's not going to change the sign. On my minus 13x squared, that would give me 2 negatives, which is a positive. So that's also not changing the sign, so that will stay negative. And that 3 is a constant, and the sign won't change, so that is also positive. So again, I have two sign changes, positive to negative and negative to positive. So there's 2. If you like the Descartes chart, we will take our positive solutions and our negative solutions, and we will also consider imaginary numbers, knowing that our total solutions for this polynomial should be 4, because that is our degree in our polynomial there, making an arrow to it, right? That's a 4. So that means we should be looking for 4 solutions, up to 4 solutions, all right? So if I put this in, positive solutions, I said we had 2. Negative solutions, we could have 2. which would give us 0 imaginary solutions. However, my imaginary solutions come in pairs of 2. So if I had 2 imaginary solutions, I could have 0 negative and 2 positive, and I'm still adding up to 4. Or I could have swapped that out. There could have been 2 imaginary solutions, 2 negative solutions, and no positive solutions. We're still adding to 4. Now, it could also be that I had 0 positive and 0 negative, and then there would be 4 imaginary solutions. I don't want that scenario because this particular method doesn't work all that well if all of my solutions were imaginary. But if I went through and I checked all of these numbers and none of them worked, then I would know that all 4 of my solutions were imaginary. Don't want to have to do that though. All right, so let's go ahead and check this remainder theorem and see. Because remember, if we get a remainder of 0, that means that that number is a factor, or it is a 0. We have an x-intercept and a factor. So let's take a look. Let's try p of 1 just because it's easy to do. If I do p of 1, that's going to be 4 times 1, which is 4, minus 13 times 1, plus 3. Gathering my positive numbers here, I get a 7. Minus 13 is a negative 6. This is not a 0. My other option is to try a positive 3. Let's be honest, I'm avoiding fractions. So this is going to be 4 times 3 to the 4th, which is 81. So I'm going to do 4 times 81, and 4 times 81 is 243. Oopsies. So I'm just going to write 243 there. Minus 13 times 3 squared, so 13 times 9. Wow, 13 times 9. That's 90 plus 27, so that's going to be 117 plus 3. If I gather my positives, that's 246 minus 107. Well, it's not 0. I don't have a calculator on me. I don't know exactly what that number is. I don't want to give up though. So that's going to be 129. Clearly not 0. Okay. So I know there has to be, or there could be a positive. I don't want to, I'm going to check. I'm going to have to check another one. So I'm going to go for the 1/2. And I'm going to hope it works. So if I do p of 1/2, and feel free to do 0.5 if you don't like using the decimal. 1/2 is 0.5. There's nothing wrong with you doing 0.5. I just like fractions. So I'm going to have 4 times 1/2 to the 4th. So that's going to be 4 times 1/16, or 4 over 16. Then I'm going to have to subtract 13 times 1/2 squared, or 13 times 1/4. That's 13/4. And then I'm going to add 3. Collecting my positives, that's going to be 52/16 minus 13/4. 13/4 is 52/16, or if you'd rather, 52/16 will reduce to be 13/4. So this is indeed 0. And I found a positive one. So 1/2 is a positive 0. I'm going to go ahead and do the negatives now because I don't want to check 3/2, 1/4, or 3/4. I mean, you certainly could if you wanted to. I'm going to avoid it. And I'm going to jump this gun, and I'm going to say if 1/2 worked, then probably a negative 1/2 would work. Might I be wrong? Yes, but I am betting odds I'm not. So I've got to do 4 times negative 1/2 to the 4th. So 1/2 to negative 1/2 to the 4th power is going to be 1/16 again. So this is going to be 4/16, just like it was for the first one. And then I've got a negative 13 times 1/2 squared, so that's going to be 13 times a 4th, or minus 13/4. And then I have the plus 3, and I ended up with the exact same thing. So that's going to be 0 again. So yes, just like our previous example, it's x to the 4th. I have found two zeros, one at 1/2 and one at negative 1/2. So that means I could use synthetic and then quadratic formula or factor the last two. So I'm going to go ahead and mark this into synthetic now. My first one I'm going to do is 1/2. And again, if you like 0.5 better, use 0.5. Nothing wrong with that. I've got 4x to the 4th. I've got 0x to the 3rds. I've got a negative 13x squared. I have 0 x's, and I have a 3. Remember to put in your placeholders for zeros. All right, synthetic division, the 4 comes down. 1/2 of 4 is 2. 0 plus 2 is 2. 1/2 of 2 is 1. Negative 13 plus 1 is a negative 12. Half of negative 12 is a negative 6. 0 plus negative 6 is negative 6. And half of negative 6 is negative 3. Oh, yes. And there's my 0. 1/2 was not as hard as I thought it was going to be. Okay. Now I'm going to swap colors. Let's go purple or green. I'm going to go green. And I'm just swapping colors because rather than start all over again, I'm going to put my negative 1/2 in. Because if they're factors, they can go in one right after each other. So this should be fine. That 4 is going to come down. 1/2 of 4 negative is going to be a negative 2. Negative 2 plus 2 is 0. Half of 0 is 0. Negative 1/2 times 0 is 0. 12 plus 0, negative 12 plus 0 is a negative 12. Negative 1/2 times a negative 12, negative is positive. Half of 12 is 6. Negative 6 plus 6 gives me 0 again. Okay, so if I look at where I am for factors, so at this point, I am at P of x. That looked like an R, but that's really a P. P of x is going to be the x plus 1/2. It's going to be the x minus 1/2. Any way you want to write it. And then I've got a 4x squared minus 12. You can do this a couple of different ways. We could use quadratic on the 4x squared minus 12. We would just have to think of it as 4x squared plus 0x minus 12. Right? And we can use our A, B, and C to do that. You can also just set this 4x minus 12. 4x squared, sorry, I forgot my squared, equal to 0. And then we would have 4x squared is 12. Divide both sides by 4, x squared is 3. And then I can take the square root of both sides, so x would be the square root of 3. But I have to include both the positive and the negative value because we don't know which one works. In which case my P of x, there we go, can be written as fully factored form x plus 1/2. I'm going to run out of room, I think. Hold on. We're going to do a little trick I learned. We're going to take all of these guys and we're just going to move it. So I plus 1/2, I need a minus 1/2. Oops. And then I'll need an x plus square root 3. And I'll need an x minus square root of 3. And this is fully factored. I still need to list the zeros. So the zeros are going to be at x equals a negative 1/2, a positive 1/2, a square root of 3, and a negative square root of 3. This is 4 solutions. Notice what we've got here is 2 positive solutions, 2 negative solutions, and no imaginary solutions. The negative 1/2 and the positive 1/2 would be rational, meaning they can be written as a fraction. And the square root of 3 and the negative square root of 3 would be irrational functions. Right? Wowza. Okay, so if I put those in my yellow boxes, fully factored is here. All zeros are here. We did the rational zero theorem to figure out which numbers we wanted to check. Descartes let us know that we could have 2 or 0 or none of each one of them. Where am I? Oh, there we are. The remainder theorem, down here in the bottom to check and see. We had to check 4 of them, but we got 2 in the last. And then we put them into the synthetic division in order to get our factors for p of x and our zeros for x. So zeros there, factors there. All right, thank you. Stick around for the next one here. Okay, I'm going to roll it on to the next one. Here we go. So the next one, we're going to fully factor a degree 4 again, only this time we're going to have imaginary zeros as a possibility. So if you were looking for a problem with imaginary zeros, here we go. Okay. Same processes. All right. Got it. First thing we want to do is use our rational zeros theorem. RZT puts our p, factors of p over the factors of q, where q is, where is it? We got green. Where q is the, p is the factors of all of our constants, our n term, and q is going to be the factors of our leading coefficient, which in this case would be a 1. So when I write these out, I'll need all the factors of a -8, and I will put those over the factors of a 1. So that's going to be a positive -1, a positive -2, a positive -4, and a positive -8. This time our q values are just going to be a positive -1. I love it when it's a 1, because then I don't get fractions usually. So what we're going to do here is a positive 1. It could be a -1. It could be a positive 2 or a -2. It could be a positive 4 or a -4, a positive 8 or a -8. And once I'm clear on what those can be, then I will look into Descartes, and Descartes' rule of signs just limits or analyzes the sign value of our polynomial so that we know how many real positive solutions to find and how many real negative solutions to find, which in turn lets us know if we should expect any imaginary. Most of the time, that's a yes. So if we look at our p of x and the signs of each term, we have a positive, a positive, a positive, a positive, and a negative. If we look at that, positive to positive, to positive to positive, to negative, we have just one sign change going from positive to negative. So we will only be looking for one positive real solution. If we consider a negative x value, for x to the fourth power, I'll have 4 negatives, which will maintain positive. For x to the third, it will switch. For x squared, it will not switch. For 4x, a negative x will switch the sign on that to negative, and then it will stay negative for that last one. That means we have 1, 2, 3 possible negative solutions. If you like the chart, you have to consider all possibilities. You can write the chart to consider all possibilities. So that's a positive, a negative, and that gives us imaginary as well. We are looking for 4 possible solutions because, again, this is an x to the fourth power. So we need our rows to total out to 4 possible solutions. We know there is one positive solution. There could be as many as 3 negative solutions. That gives us no imaginary solutions. However, our imaginary solutions come in pairs. They're called conjugates. So I could have 2 imaginary solutions, in which case I cannot take from the positives because there must be one. So that means I would take them from the negatives, leaving me with just one negative solution. So those are our possibilities. I could have 1 positive and 3 negatives, or 1 positive, 1 negative, and 2 imaginaries. And since example 3 is about imaginary zeros, I'm going to guess it's the second one, and we're looking for 1 positive and 1 negative. So let's give it a shot. We'll use the remainder theorem to go through and check our values. Check and see if anything is a factor. So let's try p of 1 just because I like to keep it simple and try the easy number first. That's going to be x to the fourth. 1 to the fourth is 1. Plus 1 to the third is 1. 1 squared is 1 times 2 gives me 2. 4 times 1 is 4. And then I have a minus 8. If I collect my positives, that's going to give me 8. Minus 8, which is indeed 0. So I have a positive 1 as a solution, and since I only have 1 positive solution, I'm not going to check any more positive numbers. I'm now going to go ahead and start checking negative numbers, because I could have 3 negative solutions, or I could have 1 negative solution. So again, I'll start with a negative 1. We'll see what that does. A negative 1 to the fourth is 1. A negative 1 to the third is negative 1. Negative 1 squared is 1 times 2 is a positive 2. 4 times a negative 1 is a negative 4. And then I need to minus 8 more. Collecting my positives, I have 3. Collecting my negatives, I have 13. That's going to be a negative 10. It ain't going to be a negative 1. So then I'll try a negative 2. All right, negative 2 to the fourth power is a positive 16. Negative 2 to the third power is going to be a negative 8. Negative 2 squared is 4, plus 2 is another 8. 4 times a negative 2 is a negative 8. And then I have a minus 8. Collecting my positives, I have a 16 plus 8, that's 24. Minus 8 minus 8 minus 8 is a negative 24. And there goes my 0. Okay, so I know that 1 and negative 2 are both zeros. since this is degree 4, I'm going to go ahead and say that's going to leave me with 2 more zeros, which I can find by factoring or quadratic. So I'm going to go ahead and use synthetic. Okay, so if I go for my synthetic division, S-Y-N-T-H, I don't think I put this on any of the others, but we'll write this as synthetic. All right, so I'm going to put in the 1 first. And my coefficients are a 1, a 2, a 4, and a negative 8. Excuse me. All right, drawing in my 0, or my line there, bringing the 1 down. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. 2 plus 2 is 4. 1 times 4 is 4. 4 plus 4 is 8. 1 times 8 is 8. Negative 8 plus 8 is 0. I wanted to get a 0 because that indicates that x minus 1 is a factor. Now, from here I can go ahead and check the negative 2. I'll put a green in there. I don't want to rewrite it. I just want to keep dividing out, the same as you would if you were doing prime factorization. So we're going to do a 1. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times 0 is 0. 4 plus 0 is 4. Negative 2 times 4 is negative 8. Negative 8 plus 8 is 0. And yes, we've got this. Now, that leaves me so far with p of x is got to equal my factors x minus 1 from my first synthetic division, x plus 2 from minus a minus 2 for my second synthetic division, and I have left here an x to the second plus 4. X to the second plus 4. Now, we can do the same thing we did in the last example and just set x squared plus 4 equal to 0 to factor this out. But I'm going to go ahead and use quadratic. In order to do that, I do have to think of this as x squared plus 0x plus 4. Then when I use quadratic, my x is going to equal the opposite of b, which is 0, plus or minus b square root of b squared, which is 0, minus 4 times a, which is 1, times c. Oops, I'm going to run out of room here. I use my little trick again. I just erased it. I should have used my little trick, but I didn't. I need to pull it over to the side. So x is going to equal the opposite of b, so that's 0, plus or minus the square root of b squared, which is 0, minus 4 times your a, which is 1, times your c, which is 4. All of this over 2 times 1, which is 2. So this is going to equal a positive or negative, because I don't need the 0 anymore, square root of a negative 16. All over 2. Now, what did we learn about the square root of a negative 16? I can pull the I out. I square root of 16. What's the square root of 16? That's going to be a positive or negative 4 times I, all of this over 2. So that's going to be a positive or a negative 2I. Okay, good. So this gives us our factors, our p of x. And again, it's degree 4, so we're looking for 4 linear factors, or 4 factors with x minus. So it's going to be x minus 1, or x plus, I guess you could say. X plus 2, x minus 2i, and x plus 2i. This gives us zeros. At x equal to 1, negative 2, a positive 2i, and a negative 2i. Degree 4 had 4 linear factors, 1, 2, 3, and 4. 1, 2, 3, and 4. And it had 4 x values, 1, negative 2, 2i, and negative 2i. Notice what we ended up with here. We go with yellow. We ended up with 1 positive factor, 1 negative factor, and 2 imaginary. 1 positive, 1 negative, 2 imaginary. 1 positive, 1 negative, 2 imaginary. Degree 4 with 4 factors. We have found all the zeros, yay us, and we have been able to write out the fully factored form. Fully factored form. All the zeros. We did our rationals. We used Descartes. We used the remainder theorem to start off with synthetic division to get the p of x and find our zeros. Thank you.